What about
Okay. Perfect. Okay. So thank you very much.
Okay, good afternoon and welcome again to the European Non-Associative Algebra seminar. I'm very glad to introduce the speaker of today, Professor Andrea Solotar from the University of Buenos Aires. The title of her talk is Tamarkin Tsygan Calculus for Gentle Algebras. Please.
Okay. Thank you very much. And again, thank you for the invitation. So I will talk about several things about the Hochschild cohomology of gentle algebras. So let me start. So my introduction. We are going to suppose that K is a field during all the talk, and that A, well, even if we are in the non-associative seminar, it will be, I think there is a problem with my screen, so give me 1 minute to check. Okay. Okay. Just a moment, please.
Okay.
Yeah. Yeah, it should be render. Okay, so yeah, it's I don't know what's happening. It's starting again, the sharing.
Okay, no problem.
Just give me 1 more minute. I will join again. Yeah. So I was saying that K is going to be a field, A an associative algebra, K algebra, and M, suppose that you have M, which is an A bimodule. Then we have the Hochschild homology and the Hochschild cohomology of A with coefficients in M. And as you know, maybe they are defined as the derived functor of the own functor for the cohomology over A. A is the enveloping algebra of A, that is by definition A tensor A of opposite over K. And it's the homology, the X of A with coefficients in M, and similarly, the Hochschild homology is the Tor functor over the same algebra, enveloping of A with coefficients in M. Okay, so they are both derived functors. So this allows us to, for example, choose any projective resolution of A for computing both the homology and the cohomology without changing the result. Of course, this is the good thing about the derived functors. Okay, so they are both are graded vector spaces. But the interesting thing is that they have a lot of additional structure, okay? So all this structure gives important invariants of the representation category, the module category of the algebra, okay? So for example, just to think a little bit about it, we have that the Hochschild cohomology of A with coefficients in A that I will denote. I will start denoting with double H of A. So if we compute it in degree 0, we just obtain the center of the algebra. If we compute it in degree 1, we obtain the derivations of the algebra, the K-linear derivations of the algebra itself divided by the inner derivations, and the cohomology in degree 2, as you know, maybe is related with the formations of the algebra. And also, well, with the homology, we obtain some invariants of this type. And as I was saying, we have the bar resolution, which is the standard resolution of the algebra A as A bimodule, but it has the problem that it is very big. And so for theoretical use, it is okay, but when we want to do computations, we need to change the resolution, and we need to find smaller resolutions, smaller projective resolutions. Okay, so the problem is that it does not change the homology and the cohomology, of course, but it changes, well, of course, the way of computing them, and it may cause a problem with the other operations that are operations in homology and cohomology, because they were originally defined in terms of the bar resolution. Okay, so let me mention all the structure we have, and this is called the title of the talk, the Tamarkin Tsygan calculus, or Tamarkin Tsygan structure for the algebra A, for the cohomology, Hochschild homology and cohomology of the algebra A. And well, it has several pieces. The first one is that the Hochschild homology is a graded commutative algebra, commutative in the graded sense, with a product that is called the cup product, that we are going to talk about this later. And if we look at the Hochschild cohomology shifted by 1, then it has a bracket, so it becomes a graded Lie algebra with the bracket that is called the Gerstenhaber bracket. The Gerstenhaber bracket is a kind of generalization of the Schouten-Neuhaus bracket to the non-commutative case, okay? So these two things together, it is what is called the Gerstenhaber structure of the Hochschild cohomology of an algebra, okay? So this is only with respect to cohomology. But then we have the Hochschild homology, and the Hochschild homology of A is a module over the cohomology. Okay. Moreover, we have a map which is called capital B, and it's the name is the Cons differential. Which goes from the Hochschild homology in some degree to the same Hochschild homology, but in the same degree plus 1. Okay, and in the same way as the Gerstenhaber bracket generalizes the notion of Schouten-Neuhaus bracket, this generalizes the notion of the RAM differential. Okay, so this is considered as a way of generalizing to a non-commutative setting things that happen in the commutative world. Okay, and then, but I'm not going to talk about this today, we have the cyclic homology of A, defined by Kohn, Lode, Tsygan, several authors at the end of the 80s. Okay, but in particular, let me just mention that it is more difficult, maybe, to compute because it is not a derived functor. So it is not so easy to compute it when we change resolutions. Well, all of this together is what is called the Tamarkin Tsygan structure of the Hochschild homology and cohomology. Okay? So, which is the problem with this? Well, the good thing is that it gives a lot of invariants, but the bad thing is that it is very difficult and, let's say, almost impossible to compute all this structure explicitly because of the change of resolution that I was mentioning. So, well, it is extremely difficult to compute it explicitly. Okay, so if we find a family which is interesting in itself, a family of algebras, and for which it is possible to compute all this, so we will be happy because we would have examples. Okay, so the first thing to say is that monomial algebras have models such that we can consider that the algebra is presented as the quotient of, this is Q is a quiver, a finite quiver. This is what is called the path algebra, or the paths in the quiver with the concatenation, divided by some ideal, okay? And the ideal satisfies some conditions to be admissible, okay? In particular, the ideal is contained in the space of paths of degrees greater or equal to 2, okay? So we have a presentation like this, and if we don't have a presentation like this, we know that we can write A as an algebra which is Morita equivalent to one of these, okay? So the fact of being monomial means that we can find a monomial set spanning I, okay? So we call the elements of this set the spanning relation, the relations of the algebra A, I want to say. Okay, so this is a good situation because in this situation, what is called the minimal resolution, smallest possible one with arrows into the other resolutions, the minimal resolution of A in this case is well known, both the modules and the differentials, because it is what is called the Parcells resolution. And it is described very well, okay? But even if the resolution is small and is described very well, it is still very difficult to compute in general all these invariants. So the next reduction that we are thinking about is what happens for quadratic monomial algebras. So the generators of the ideal are not only monomials, can be found not only as monomial, but as quadratic monomials, okay? Then for this kind of algebras, it is possible with a lot of effort to compute all the Tamarkin Tsygan structure. So in particular, we will be interested in a family of algebras which are quadratic monomial, and moreover, they satisfied more conditions, and these are called the Schendel algebras. So we will be interested, that I will define soon, interested on Schendel algebras. As I said, they are quadratic monomial, But why are we interested on this kind of algebras? Because they are related with several areas in mathematics and in mathematical physics. In mathematical physics, with string theory, there are some models that can be described using gentle algebras. And in particular, they have, or there is, a geometric model associated to each gentle algebra. But I will explain what do I mean with this, okay? And so the idea is that we are going to see all the elements in the homology and the cohomology, not only in terms of the quiver of the algebra A, but also in terms of the curves that appear in a surface that is associated to the gentle algebra. Okay. I don't know if there is any question. In case you have questions, please feel free to interrupt me. Okay. Well, and we are not only going to see the elements generating the homology and the cohomology, but we are also going to see the operations in terms of curves. Okay. So let me talk a little bit about gentle algebras. Okay. So gentle algebras, very brief definition, and let me recall some things. They were defined in the 80s by Assem, Happel, and Skowronski to study some problems in representation theory. They are tame algebras. This is related to how many ISO classes of representations of the dimension D for each D we have. They are given by uniparametric families, several ones, okay? And they are in the composable models are described. So they have a lot of good properties. And they have, as I mentioned, connections with mirror symmetry, string theory, etc. So a very brief definition of gentle algebra. Suppose that that my algebra has a presentation Qi. Q is a quiver. I is the ideal of relations. That means that A is KQ divided by I. Okay. If I have this presentation, the quiver will not change, but the ideal will change, may change. Okay. So this is why I call it a presentation. So given a presentation like this, I has to be monomial, and I is going to be generated by quadratic monomials. Okay, and locally, suppose that I have any vertex in Q, I will denote the vertex is by Q0, then at each vertex, there are at most 2 arrows arriving at that vertex, maybe less, maybe 1, maybe none, and at most 2 arrows going out, okay? Again, maybe none, maybe 1, okay? But moreover, if, for example, I arrive with this arrow and I don't have 2 possible ways to continue in a non-zero way, okay? So, for example, one of them, I have to ask it to be a 0 composition, okay? And the same for the other. So this one, for example, I arrive here and cannot go out in a non-zero way in two different ways. So for example, I ask this composition to be zero, okay? So this is, in a very brief way, the definition of a Schendel algebra, okay? So, any question? Perfect. Okay, so let me talk a little bit about the geometric models how to associate a geometric model to a Schendel algebra given a presentation, okay? So suppose we start with a presentation of our algebra A, that means, again, a quiver and the ideal of relations, and suppose that is a Schendel presentation, so satisfying what I have just mentioned, okay? So from this, I'm going to associate to it, let me call one this procedure. I will associate something that is called a marked ribbon graph. I will explain it in a moment, okay, with an example. And to this, once I have this marked ribbon graph, let me call it G, it is possible to associate to it what is called a marked ribbon surface that we are going to call SG, okay? So here in the presentation of the algebra, we will have elements that will allow us to describe homology and cohomology. And we are going to see these elements spanning the homology and the cohomology as curves in this surface. This surface also comes with a dissection, okay? Okay, so let me give an example. Let me first say what is a marked ribbon graph, G. So a marked ribbon graph is a finite. I am not asking the algebra to be finite dimensional, okay? So a finite undirected graph with a given cyclic ordering where on the set of edges adjacent to each vertex, okay, and a mark. So let me do it in an example to make it a bit more clear, okay? So suppose that we start, so example, suppose that we start with this algebra. We have a quiver with 1, 0, 1, 2, 3, 4 vertices. And then we have arrows here, alpha 0, alpha 1, alpha 2, alpha 3. And we have relations. So for example, the composition here is 0, so alpha 2, alpha 1. This is the one relation. And the composition here is 0, so alpha 3, alpha 1, alpha 3. Okay? Okay, so these are the relations. This is a Schendel algebra. For example, let me look just as an example at this vertex 1. There are 2 arrows arriving, so less or equal than 2, and only 1 arrow going out. So, for example, I arrive with this condition I forgot to mention, that when I have, for example, this arrow alpha 1, there are 2 arrows, alpha 0 and alpha 3, preceding it. So only one of these paths can be non-zero in the algebra. So here the only one that is non-zero in the algebra is alpha 1, alpha 0. Okay? I forgot to mention this condition. Okay. So we have this algebra, and in order we want to construct the ribbon graph Xi. Okay, this is our question. So for this, the first thing we look at is the set of maximal paths in the algebra. And in this case, for example, I start with alpha 0, and then I can continue with alpha 1, but then it stops because I have a relation here. So alpha 2, alpha 1 is 0. So alpha 1, alpha 0 is the maximal path. And in the same way, alpha 3, alpha 2 is the maximal path. Okay, these are the only maximal paths. So which are the vertices of the ribbon graph Xi? Well, it is the set M of maximal paths union the set of those vertices in Q such that they belong to only one maximal path. Okay, so in this case, it is going to be, well, M, which is alpha 1, alpha 0, alpha 3, alpha 2, and then we have to add two vertices, the vertex 0 and the vertex 3, because they belong just to one maximal path. The vertices 1 and 2 do not satisfy this condition, okay? So let me place these vertices of my graph Xi. So here I will put the 0. Here I will put alpha 1, alpha 0. Here I will put 3. And here I will put alpha 3, alpha 2. Okay? So how to construct the edges of the graph Xi that I am constructing? So the edges of Xi are in one-to-one correspondence with the vertices of Q, of the quiver Q. Okay? So, but where do I put them? Well, for example, the edge corresponding, let's say, to the vertex 0, well, it will be linking those points here in the graph Xi that are points, let me draw it. So they are only these ones, because the vertex 0 in the quiver, well, of course, passes through 0, and this is a path through 0, through the vertex 0. Okay, so I put here 0, the same here, I put the edge corresponding to the vertex 3, and then what happens with the vertices 1 or 2? Well, the vertex 1 belongs both to the path alpha 1, alpha 0, and to the path alpha 3, alpha 2. So I put it here. And the vertex 2, well, it is the same. Okay? So the only thing that is missing is giving a cyclic ordering in the edges here that are adjacent to a vertex. So when there is one, we'll have nothing to do. But for example, in this place, alpha 1, alpha 0, the vertex alpha 1, alpha 0, I have 3 edges that are adjacent. So I go from one to the following one, just following the path. Okay, so this is alpha 1, alpha 0. So I go with alpha 0. In general, we don't write alpha 0 here. That goes from 0 to 1. And then with alpha 1 from 1 to 2. And then we complete it to make it cyclic. And here we put a mark, okay, where the path ended. So on the other side, I have alpha 2 going from 2 to 3, and then alpha 3 going from 3 to 1, and then I complete here and I put the mark. Okay, so this is the mark graph Xi that I obtained. Okay, from this one, the procedure is to obtain a surface, okay? And the surface is obtained, well, this is not so nice to see, but I take each of the vertices of G that have more than one adjacent edge, and, for example, alpha 1, alpha 0, it has 3 adjacent edges, so let me draw something like this, kind of hexagon, and then I will have 0, which goes to 0. So I'm looking at the graph sheet 1, that goes to alpha 3, alpha 2, and 2, that also goes to alpha 3, alpha 2, and I am going to glue these two together, okay? So this is for this vertex. For the other one, for alpha 3, alpha 2, it also has 3 adjacent edges. So I will put here, this is 1 goes to alpha 1, alpha 0. Then I have 3 that goes to 3. And finally, I have 2, which also goes to alpha 1, alpha 0. And then I'm going to glue these two, okay? And so this alpha 3, alpha 2, I'm going to glue it with an orientation, the opposite orientation, to the point that I obtain gluing these two. Well, and this will give me a surface. And within this surface, I will be able to recognize the graph sheet, okay? So the idea is that, let me write it, the isoclasses of Schendel algebras are in one-to-one correspondence with the surface dissections, okay? So in order to study Schendel algebra, several things can be done. That is, studying the algebra itself or studying the surface, and we obtain what is called puncture surfaces, okay? So my aim, I forgot to mention, this is a work in collaboration with Sibylle Scholl, Christian Chaparro, and Mariano Suarez Alvarez. We started the job of studying the cohomological and homological invariants and relate them with the curves in the surface that is obtained associated in this way to an algebra, okay? Okay, so now I will start describing what we obtain for Hochschild cohomology. Okay. So I will just give you the generators as a vector space of the Hochschild cohomology that we obtain in each degree. I am not doing the explicit computation because it will be too long. So suppose that we have an algebra A, and we have that this Qi is a Schendel presentation. So the Hochschild cohomology of A is generated as a vector space by the following. So we have several types of classes. The first one is what is called the one, the unit. It is the unit of the algebra, and it corresponds to a sum corresponding that I will denote EI parallel to EI for I, a vertex. okay? So, oh, there is some problem again with my screen. So just let me check what happened, sorry, again. It is reconnecting. Well, in the meantime, let me explain. Yeah, here it should be. Just a moment, please. Oh, I'm sorry for the connection today. It's a problem. Let me try to do something. Okay, let me try to share the screen. Oh, sorry. I cannot find my screen. Yeah, here it is.
Okay.
Okay, thank you. Sorry. So I was saying that I'm denoting this parallel path because the cohomology, in all the cohomology, the things that we are computing corresponds to path in the quiver. For example, let me go to the quiver, to the example we had before. Here we have that, for example, of course, each vertex is parallel to itself, each arrow is parallel to itself, but for example, here, in the graph, the composition of first alpha 1, then alpha 2, and then alpha 3 is going to be parallel to this vertex, okay? If I have, for example, a graph like this one, ABC, so the path BA is going to be parallel to C, okay? Well, and in the cohomology, in degree 0, where we will have a unit element, so this will belong to HH0, to the center of the algebra, of course. But we may have more elements in HH0, and so the second family of elements is going to be the the source of path alpha and the path alpha, such that the path alpha is not 0, so it is in the basis. The basis of the path of the algebra A, we are going to call it B, it's given by classes of paths. And we say that it is B maximal. That is, if we add any other arrow following or preceding alpha, it is going to be 0, okay? So this is also an element in HS0 of A. And a third family, and this third family, we are going to call it, again, alpha with some brackets. But now, alpha is also going to be a circuit, and I will write it like this. A circuit will be something like this, for example, and we can rotate it. So this is why I'm taking classes. And it will be in the basis of the algebra. And it will be of period R, let's say, the period here is 4 in the example. And it is a sum from 0 to R minus 1 of elements that are the source of the rotation I times of alpha parallel to the rotation, to the corresponding rotation, okay? But this is, even if this is an element in HH0 also, it does not appear, or let me say that it only appears when the dimension of A is infinite, okay? Because if not, we cannot have things of this type, okay? So this already allows me to find if the dimension of the algebra is finite or not, okay? Then we have other elements in the cohomology, and these elements are very important. This is arrow parallel to arrow, so here C is an arrow in the quiver, and it is in the complement of a spanning tree, of the spanning tree that we have chosen, okay? Oh, sorry, you can have problems with the connection. So let me do something. Just a minute, please. I don't know what happens with the connection today. Okay, so now it's okay. So at the first glance, it is one may think that they depend on the spanning tree that we have chosen, but this is not true. Okay, so we have this type of element that is in HH1. And again, we have another type of element that are in HH1, and it is the same arrow C parallel to a path C alpha, where again, this alpha is a circuit, a chosen circuit that it is in the basis. So again, this is in HH1, but it only appears when the dimension of the algebra is infinite. Okay? So after this, we have three more types of elements in higher degrees that may appear or not. So let me briefly mention them. We have a path gamma parallel to a path alpha, where alpha is a path that is, let me call it in gamma. That means that it is full of relations, or it is complete, okay? So gamma is a path like this, gamma 1, gamma 2, up to gamma n. And there are relations in each composition, okay? Let me put it one more. Okay. And the thing is that alpha and gamma do not share the first arrow nor the last arrow. Okay, they start and they end with different arrows. Okay. And then there are two other types of elements. And these other types of elements correspond to, there are two types of elements that, let me say, that they come from what we call the complete circuits. And the complete circuits are, of course, circuits where all the compositions are zero, okay? They are overlapping relations. But the important thing about these two parts, these two types of elements, is that they only appear if the global dimension of the algebra is infinite, okay? So a corollary of this description, first corollary, is that the following things are equivalent. So the first thing is that the dimension as a vector space of the algebra finite to be finite is equivalent to the condition of the dimension of the first Hochschild cohomology, the zero Hochschild cohomology space, to be finite, and this is equivalent to the dimension of the first Hochschild cohomology space being finite, and this corresponds to the fact that there is no complete, so complete is full of relations, cycle in co-complete, sorry, this is without any relations, in the quiver Q, okay? So we can recognize easily from the quiver or from the Hochschild cohomology in degree 0 or 1 if the algebra is finite dimensional or not. And we have something similar for the global dimension of the algebra. That is that the global dimension is finite. Second condition is that the cohomology stops somewhere. And the third condition is that there is no complete cycle in Qi, in the presentation Qi, okay? So when we saw this, well, it was interesting because already looking at the cohomology, we were able to say that the dimension of the cohomology was finite if and only if the global dimension of the algebra was finite, and moreover, the dimension of the algebra as a vector space was finite, okay? So Hochschild cohomology gives me information about this thing. So there we started thinking that it would be interesting to compute other homological or cohomological invariants. So we compute the Hochschild homology that I will not have time to describe. And I have to say that the Hochschild homology gives some information, but most of the interesting information is encoded in the cohomology, the cup product of the cohomology, and the Gerstenhaber structure, okay? So since I do not have such a long time, let me go to the Gerstenhaber structure, okay? So the Gerstenhaber structure. The Gerstenhaber structure is the following. So let me recall that you have the Hochschild homology, and you have a bracket such that for each n and each r, the bracket, which is satisfying the Jacobi identity and satisfying graded anticommutativity, goes from here to n plus r minus 1 of A. And this is why, in order to have a graded Lie structure, we have to shift by 1, okay? But in particular, if we look at what happens in degree 1, at the bracket in degree 1, we are going to fall again in degree 1. And this is why this part is a Lie algebra in itself. It's the algebra of derivation modulo inner derivations. Okay, so we have computed all this structure, and the thing is that the interesting part, the non-trivial brackets, amongst generators of the graded algebra of the Hochschild cohomology with the cup product are given by brackets with these elements that we call diagonal elements. That is, C is an arrow, and it does not belong to the spanning tree. So if we compute the bracket of this with another element in cohomology, we will obtain that it is a multiple of the element. This is diagonal action, And here it is the degree in B of C, which has to do with the number of times that C appears in the cocycle B. For example, if you have that in the cohomology, one element is this path, which is with relations alpha 1, 2, 3, that is parallel to the path, let's say, beta 1, alpha 2, beta 3, and here we have no relations. So in this case, the degree, and this is C, the degree of this element B in C will be 0, because we will have 1 in this part, the part with relations, minus 1 in the part without relations, okay? If, for example, this is not C and the path is a bit different, so we have beta 1, beta 2, beta 3 without relations, and suppose that now this one is C, so here the degree in C will be 1, okay? So it's easy to compute it. And these are the only, let's say, non-zero generated brackets. So the theorem about the cohomology is as follows. So suppose that the quiver Q is neither a loop nor what is called the Kronecker quiver. In these cases, we can compute the Lie structure very easily. For example, if Q is the Kronecker quiver with arrows A and B, so here we will have Hochschild cohomology only in degree 0, in degree 1, and in degree 1 we will have 3 elements, 3 different classes, A parallel to A, B parallel to A, and A parallel to B. We don't have B parallel to B because it will be equivalent to A parallel to A. And the existence of these 3 elements will give me that the Lie structure of HH1 is isomorphic to SL2, okay? Because of the computation of the brackets. So this is a case we are excluding here. So suppose that it is neither a loop nor the Kronecker quiver. So the graded Lie algebra Hochschild cohomology of A shifted by 1 is isomorphic to a product of Lie algebras, L1 times LR, let's say, where this R is exactly the number of cycles that we will call Ki in the underlying graph of Q, okay? So how do we describe this L1 up to LR, okay? The description is as follows, and it depends on the configuration of the cycle, okay? So the idea is the following. Let me just look at it. Yeah, we have 4 types. Li is or belongs to one of the following 4 types. First case is when the part of the graph, the cycle corresponding to Li, is locally, so we just look at this cycle, and it's locally a Kronecker quiver. So it is a Kronecker, but it's not the only Kronecker, sorry, in the quiver. Okay, so in this case, Li is very easy. It's just one-dimensional. So the Kronecker, let's call it AB, but there are other things. So it is Li is spanned by this. The second case is when the cycle Ki is locally of type what I call gamma parallel to alpha. So I have gamma, a path, and alpha, another path. They are parallel, and here it is full of relations. Okay? So in this case, this gives me an element in cohomology, and the algebra, the Lie algebra Li, is going to be spanned by this thing, gamma parallel to alpha, and all the pairs A parallel to A, such that A is an arrow, which is not in the spanning tree, and A belongs either to alpha, or A belongs to gamma, or belongs to alpha. Okay? So in this case, we have that this is the Lie structure, and the action between AA and the gamma alpha is diagonal, as I described before. So this is the second type. The third type is that the case when Ki is locally of type gamma, and this is going to be now a cycle which is full of relations, and it is parallel to the source of gamma. Let's say that this is the vertex source of gamma, and in this case the Lie algebra is going to be spanned by some elements that we call, we have infinite elements, an infinity of elements like this that we call gamma k for each k. And this corresponds to going around gamma k times, okay? And then another pair, A gamma k for each k, sorry. A gamma k parallel to A for each A in the complement of the spanning tree, and of course A in gamma, okay? So which is the Lie bracket here? Well, the bracket of this element, alpha k, with A gamma k parallel to A, we obtain it using the Leibniz identity. So let me put it's not necessarily the same k, but it's going to be an L here. Is we obtain the element gamma k plus L. Okay? Okay, so this is the Lie structure here, and the last one is when the cycle Ki is locally. Now we have that we have on this side alpha, which is a cycle without relations, and here we have the source of the cycle, okay? And in this case, Li is going to be spanned by some elements that I will still denote, well, here alpha k for k an integer, and that will be going around this cycle k times. And again, A parallel to A alpha k for all k, where A is an arrow which is not in the spanning tree, but here we have one more element, let me put parallel, which is A parallel to A. And the brackets are obtained in the same way, using the Leibniz identity and using the diagonal action of this element of the Hochschild cohomology in degree 1 with the others, okay? So here we have all the Lie algebras that we can obtain when we compute the Gerstenhaber structure of a general algebra itself. So we will obtain a product of all these, one for each cycle in the underlying graph. Okay? This will give us also some information about the quiver, some information about the presentation of the algebra, and some information about what happens and how do curves concatenate in the surface. Okay? Well, this is only a little bit of a structure, but since I am out of time, I will stop here. So thank you very much.
Thank you very much for your interesting talk. Are there any questions? Comments or remarks?
Okay, so there is a question. Yeah.
On the chat, yeah.
Yeah.
Okay, thank you very much. Please suggest connections to coalgebras.
Connections to coalgebras.
A few comments on
the comments on Jacques, I suppose is the comment because, well, a lot of things about the Gerstenhaber bracket have been studied by both Gerstenhaber and Jacques. I don't have a lot of comments about it, but just to say that how the Gerstenhaber bracket appear, and the Gerstenhaber bracket appear long before, just to obtain a proof of the graded commutativity of the Hochschild cohomology. And then, as I said, Gerstenhaber and Jacques worked a lot on it and on Hochschild cohomology. But I don't have connections to coalgebras. I'm sorry. I'm not. I have not developed this side. Thank you.
Thank you. Other questions? Okay, if not, let's thank the speaker again.
Thank you.
And okay, we will resume on next Monday at the usual time. Bye-bye.
Bye-bye.